Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
Imagine an invisible thread connecting you to your drone, the command link that makes it fly, capture photos, and execute complex maneuvers.
Yeah.
But what happens if that thread phrase, or worse, snaps entirely? Today, we're pulling apart the critical systems and procedures that manage that invisible connection, the command and control link, and, the essential safety net known as fail-safe.
That's right. And we've gathered quite a stack of resources for this deep dive. We're looking at everything from the bedrock Canadian aviation regulations, CR 901 specifically, to the practical guidance in Transport Canada's TP 15263.
Okay.
Plus insights from expert operational guides and, lessons learned from real-world scenarios. This isn't just about the tech specs, it's really understanding the regulatory expectations and the absolute best practices to keep your advanced drone ops safe and compliant.
So our mission is clear then. We want to unravel the complexities of how your drone talks back and forth with you, identify the things that threaten that communication, understand the drone's automatic emergency responses, and, maybe most importantly, clarify your inescapable responsibilities as the pilot in command. Think of this as your essential training, maybe your shortcut to not just understanding Section 2.1.3 of the Advanced RPAS exam, but truly flying like a pro who anticipates problems, not just reacts.
Exactly. It's about moving beyond just operating the sticks to understanding the underlying system integrity, knowing the consequences of failure, planning intelligently to prevent it, and behaving professionally when it does happen. This is fundamental stuff. Let's unpack this.
Okay, let's really dig in. At its heart, what exactly is this command and control, or C2 link we hear so much about? It does sound a bit military, which I guess makes sense given the history. But for a drone pilot today, what are we actually talking about?
You're right. The term definitely has military roots, command structures, and all that. But in the drone world, or RPAS as the regs call them, the C2 link is essentially the sophisticated two-way radio communication system. It's between your ground control station, usually your controller, could be a laptop, maybe even a dedicated console, and the aircraft itself.
Okay.
It's basically the digital conversation that lets you direct the drone and, crucially, lets the drone report back to you.
A conversation. So it's not just me shouting orders one way.
Not at all. It's absolutely a two-way street, and both directions are, frankly, equally vital. First, you've got the uplink. That's the stream of data carrying your commands from the controller to the drone.
Right, my stick movements, camera triggers.
Exactly. Every stick movement, every switch flick for flight modes, telling it to take a picture, starting an automated flight plan, hitting return to home, that's all going up on the uplink. And then flowing the other way, you have the downlink. This is the essential data stream coming back from the drone to your ground station. And this data, collectively, is called telemetry. Telemetry. Okay, so that's all the numbers and gauges I see flashing on my screen. Battery percentage, GPS lock, altitude, speed, heading, attitude, and, I guess, critically, the signal strength for this C2 link itself.
Precisely. Telemetry is your lifeline of information. It's the drone's status report back to base. And the sources, especially Transport Canada's guidance, are super clear on this. For regulatory compliance and safe operation, a valid C2 link needs both. It needs the control commands going up and the essential telemetry data coming back down.
Both.
If you lose either one of those, you've effectively lost your reliable C2 link.
Okay, uplink for commands, downlink for telemetry need both. Why is Transport Canada so focused on this? What's the specific rule that drives this need for a continuous, reliable, two-way connection?
The fundamental rule here, the one that really underpins so much of advanced RPAS operations, is CRR 901.31. This reg puts a direct and, unambiguous responsibility on you, the remote pilot, to maintain a continuous and reliable command and control link at all times during flight. At all times. That phrase feels pretty strong. It's not just when I'm actively flying manually.
Nope. The regulation specifically says during flight. That means from the moment those procs start spinning for takeoff until they stop after landing. Every single phase.
Wow.
Whether you're hand flying, running an automated waypoint mission, or just sitting there in a hover, that link must be continuous and reliable. And here's a point the sources really flag as critical, and it's a major area the exam loves to probe. If that C2 link becomes unreliable at any point during the flight, you must discontinue the operation.
So wait, I can't just, tough it out. If my signal bars dip into the yellow or red, or my telemetry kind of freezes for a second, I can't just keep flying my grid and hope it clears up.
No, that's the crucial bit. The regs and the guidance, they're clear. Once the link's integrity is compromised, even just for a moment, the safety of the whole operation is questionable. You can't just see the signal pop back up a few seconds later and, hit resume mission like nothing happened. Losing reliability means you stop the planned operation. You either need to land immediately, or if you do manage to get the link back strongly, you have to do a thorough check, verify the system's integrity before you could even think about continuing. But honestly, often the safest, most compliant move is just to land. That momentary loss, it's a big red flag you just can't ignore.
It really sounds like this emphasis on a reliable link, especially including the telemetry, must be a lesson learned the hard way. Where did this whole C2 concept even start in the drone world?
Well, like you said, the term C2 itself is straight out of military command doctrine from, the 1960s. When the early UAVs started popping up, especially in the 80s and 90s, that military term for the pilot-to-aircraft communication just kind of stuck.
And the early systems were pretty basic, I imagine.
Oh, yeah. Often just basic analog radio control, kind of like fancy hobby RC planes back then, and they were notoriously prone to interference.
And often didn't have that feedback loop, the telemetry.
Exactly. That was a huge issue. Many early systems, they just didn't have a robust telemetry downlink. Operators were often flying just based on what they could see, maybe a grainy video feed if they were lucky. But with no real-time data on where the aircraft actually was, its altitude, battery, system health, they were essentially flying blind regarding the drone's own status.
And what was the consequence of not having that telemetry? What happened?
Well, the sources point to some pretty significant incidents, especially in military ops back in the 90s and early 2000s. Pilots would lose that downlink data, right?
Yeah.
And even if they still had some basic control over the aircraft's movement, without knowing its position or altitude or how much juice it had left, they'd get disoriented. They couldn't make safe calls, and frequently that led to losing the aircraft. Crashes. Telemetry is basically your eyes on the system's internals. Without it, you've lost critical situational awareness. These hard lessons directly shape the regulations, like Canada's CR 901.31, demanding continuous, reliable communication. They understood that includes the aircraft talking back to you.
So it wasn't just about sending commands out. It was about the drone confirming, yep, got it, and here's my status. And keeping that reliable two-way link going, that must have become a real challenge as drones started flying further or being used in more complex places.
Oh, absolutely. The sources really highlight this. When Transport Canada was first looking at commercial beyond visual line of sight ops, BVLOS, back around, say, 2016, 2017, the single biggest hurdle wasn't the drone's ability to navigate on its own or its camera quality. It was proving the reliability of the C2 link at those extended ranges and in all sorts of environments.
Really? That was the main thing?
Yeah. Operators trying to get the necessary approvals, those SFOCs or advanced compliance declarations, they had to show really rigorous testing of the link. They had to predict its behavior, prove they had enough signal margin, buffer. The C2 link reliability and the fail-safe connected to it was, and frankly still is, a fundamental gatekeeper for anything advanced like BVLOS.
Okay, wow. So the C2 link, this invisible two-way conversation, military routes, locked into regs like 901.31 because of tough lessons learned. But what happens in that moment when, despite all your planning and monitoring, that invisible leash does go slack or just snaps?
Right. That's where the critical safety feature called fail-safe jumps in. This is the drone's pre-programmed automatic response when it detects it's lost that C2 link. And CR 901.34 specifically mandates that your RPAS must have a system that automatically detects that C2 loss and initiates a safe response.
So it's the drone executing an emergency plan that I've set up beforehand.
Exactly that. When the drone figures out, hey, I'm not getting commands reliably anymore, and maybe they're not getting my telemetry either, it needs a plan to minimize risk. Most professional drones give you several common fail-safe options that you, the pilot, configure before you even take off. The one most people know is probably return to home, RTH. In this mode, if the link drops, the drone basically turns around and flies back to a designated home point.
Which is usually where I took off from.
Usually, yeah. It's typically recorded automatically by GPS when you arm the motors, or sometimes you can set it to follow the controller's current location. Critically, it usually climbs to a preset altitude you define before heading back, which is vital for clearing obstacles. RTH is generally a good choice for wide open areas without too many tall things around. Okay, another common one is hover in place. If the link cuts out, the drone just uses its GPS or other positioning sensors to hold its current spot, its current altitude.
Why would that be useful?
Think complex or tight environments, maybe indoors, flying under a bridge, or deep inside a city block between buildings. In those cases, trying to fly back automatically might be more dangerous than just staying put. Hovering gives you a chance to maybe reposition yourself, fix the interference, and regain the link without the drone potentially hitting something on an automated return trip. And then there's land in place. If you set this, the drone just immediately starts coming straight down and lands right where it is when it loses the C2 link.
Okay.
This is often the safest bet for really confined spaces, like inside a warehouse, or maybe if you absolutely cannot risk the drone moving horizontally, perhaps because of hazardous zones nearby.
Right, so the drone has a failsafe. I pick one of these, RTH, hover, land. Does that mean I don't know, pick RTH because it sounds good, set the altitude really high to clear everything, and then just set it and forget it?
And that is right at the core of your responsibility under 901.34. And it's another huge point the sources flag as a common mistake, and definitely something the exam tests. You, the remote pilot, are 100% responsible for choosing and configuring the fail-safe behavior that is appropriate for the specific circumstances of that particular mission in that specific airspace over that specific terrain.
So it is absolutely not a set it and forget it feature using whatever the factory default was.
Definitely not. That's a critical misunderstanding. The sources are crystal clear. Just relying on the factory settings or using the exact same fail-safe parameters for every single flight, no matter where you are, that's considered negligent. It's non-compliant for advanced ops.
Wow.
The drone will do precisely what you told it to do in its fail-safe programming, even if that action leads straight into a violation or an accident. Your fail-safe settings have to be deliberate, conscious choices tailored to that specific flight environment.
My fail-safe setting could actually cause a violation. How? Give me an example.
Okay, this is a classic exam scenario. The most common way your failsafe can cause trouble is with the RTH altitude violating airspace rules. Let's picture this. You're flying legally, doing maybe a roof inspection, inside the lateral boundaries of controlled airspace near an airport. Let's say this airspace, Class C perhaps, starts at 400 feet above ground level right where you are.
Okay, 400-foot ceiling.
Right. And you planned your flight carefully at 300 feet AGL, well below that ceiling. But when you set up your RTH failsafe altitude, you decided to punch in 500 feet AGL. Maybe you're thinking about some tall trees way back near your launch spot, or you just thought higher is always safer.
Okay, so I'm flying at 300 feet legally, and then I lose the C2 link.
Well, the drone triggers RTH, and the very first thing it does, because you programmed it to, is start climbing towards 500 feet.
Oh, no.
Exactly. As it climbs, it busts right through that 400-foot ceiling of the controlled airspace you were operating underneath. That action, caused entirely by your failsafe setting, is a clear violation of CR 602.02, the rule about obeying airspace restrictions. The failsafe worked perfectly.
But I told it to do the wrong thing for that location.
Precisely. It highlights that your failsafe altitude, especially for RTH, needs really careful thought. It has to be high enough to clear the actual tallest obstacles between the drone's furthest point and home buildings, towers, hills. But it also has to be set below any controlled airspace ceilings or other restricted zones you aren't allowed to enter during that automated return flight.
So every single time I fly, I need to know the tallest obstacles A&D, the airspace limits for that specific area before I finalize my failsafe settings.
Yes, absolutely. The sources hammer this home, identifying those obstacles and understanding the airspace, its class, its boundaries, its floors and ceilings. That's a mandatory part of your pre-mission planning as an advanced pilot. Your failsafe configuration flows directly out of that site survey. And it's not just airspace. Another angle comes from CR 602.41, the general safety rule. Your failsafe action must not endanger people or property on the ground either. So you can't program land in place if your flight path takes you over a busy road or a crowded park, because losing the link there would mean the drone tries to land unsafely right on top of things.
Okay, planning the right failsafe is critical. But what about making sure it actually works? Does the rule say anything about testing it?
It does, yeah. CR 901.34 explicitly states that the failsafe behavior must be tested prior to flight. Now, some might read that minimally, but the guidance in TP 15263 and just the general expectation for professional advanced operators is clear. You need to confirm that the failsafe you set up actually triggers correctly and starts doing the right thing.
Like making sure RTH actually tries to go home at the right altitude.
Exactly. Or confirming that hover mode engages, or that land mode starts descending. Many modern controllers or apps actually let you simulate a C2 link loss while the drone is still safely on the ground, specifically for this test. If you skip this test and then an incident happens where the failsafe didn't perform as you thought it would, well, you're looking at serious noncompliance and potentially increased liability.
It's fascinating, isn't it? This automated safety feature, failsafe, it actually puts so much responsibility back onto the pilot's active knowledge, planning, and verification. You really can't just rely on the automation blindly.
You absolutely cannot. You need to know, inside and out, how your specific drone's failsafe works. You need to verify it's configured appropriately for the specific mission. You need to test that it functions correctly. And you need to be ready to monitor what it does if a link loss actually occurs during flight.
All right, this is making sense. We've got the required continuous C2 link, the pilot configured failsafe as a backup. But let's talk about the real world. What are the common things out there that actually cause that carefully managed link to degrade or just poof, disappear? What are these signal killers?
Yeah, this is where operational awareness really comes into play. Knowing the threats helps you predict problems and plan around them. The sources give us a pretty good list, and TP 15263 expects advanced pilots to recognize these and mitigate the risks.
Okay, let's break down that list. What's the biggest, most obvious one?
I'd say physical obstructions. The radio frequencies typically used for drone C2, especially the common 2.4 and 5.8 gigahertz bands, behave a lot like light waves. They really need a clear line of sight, or LOS, to travel effectively.
So anything solid getting in the way?
Pretty much. Anything dense between your controller antennas and the drone's antennas can block the signal or weaken it significantly. Think flying behind big buildings, you get urban canyons, where the signal might bounce around confusingly. That's called multi-path interference. Or the building just flat out blocks the direct path.
Trees, too.
Oh yeah, dense trees are surprisingly effective blockers. Especially if the leaves are wet from rain, the water absorbs the radio waves really well. Hills, ridges, cliffs, even large metal objects like parked trucks or big industrial tanks can create signal shadows. A classic scenario the sources mention. You're inspecting something, maybe a pipeline that goes over a hill and down the other side. As soon as the drone drops below the ridgeline, out of your direct sight,
Signal drops.
Signal plummets, maybe triggers RTH. The risk was predictable LOS obstruction. The expert move is to pre-plan your flight path to stay above the ridge, or maybe fly a pattern around the terrain feature to keep that line of sight open. Or another one, mapping a construction site surrounded by tall steel frame buildings. As you fly your automated grid pattern, you notice the signal flickering, maybe dropping out momentarily as the drone passes behind a concrete pillar or a steel beam.
Yeah.
Risk there is both the physical blockage and that multipath interference from all the reflective surfaces. The expert action, maybe break the mission into smaller segments where you can maintain LOS for each part, or accept shorter flight legs. And if you do see that momentary loss, you pause, you verify control robustly, or you land if you're uncertain. You don't just press on hoping for the best.
Okay, so the physical environment itself is a huge factor. What about invisible stuff? Like other radio signals messing with mine?
Absolutely. Electromagnetic interference, EMI, and radio frequency interference, RFI. These are huge and often harder to predict precisely. Basically, it's background radio noise or strong signals from other sources that can swamp or corrupt your drone's C2 communication. TP 15263 specifically calls out needing to understand and mitigate these.
What kind of things cause this EMI or RFI?
Well, the sources list several big ones. High voltage power lines and electrical substations are notorious. They can generate a lot of broadband electrical noise. Radar installations, like at airports or military bases, emit powerful pulses that can definitely interfere, sometimes right in the drain frequency bands.
Cell towers.
Cell towers are another big one. They're broadcasting strongly, often sharing or adjacent to drone frequencies. This is especially relevant if your drone uses an LTE link for control or backup. You have to manage handoffs between towers, deal with network congestion. Even old AM radio broadcast towers, they pump out incredibly powerful broad signals that can cause unexpected glitches.
And Wi-Fi.
Yeah, dense Wi-Fi networks, especially in urban areas, using that crowded 2.4 gigahertz band, just raise the overall noise floor, making it harder for your drone signal to get through cleanly. Plus, some heavy industrial equipment can generate significant RF noise, too.
So a scenario, I'm inspecting near a big electrical substation, and suddenly my signal bars are bouncing all over the place. Maybe the controls feel a bit laggy.
Right. Risk. High EMI is degrading your C2 link, could cause errors or total loss. Expert action. Immediately increase your distance from the interference source. See if the link stabilizes. If you can't restore a reliable link, abort the mission. And critically, log that event, note the location, the suspected source, so you can plan better next time.
Or if I'm planning a flight near, say, an airport radar or a known powerful radio tower.
Then your pre-flight site assessment must identify those potential RFI sources. You need to plan your flight path to maintain a really safe standoff distance, could be hundreds of meters, maybe even more, depending on the source's power. And if you do have to operate near such areas, you need to be hyper-vigilant, watching that signal quality like a hawk, ready to back off instantly at the first sign of trouble.
Man, it seems like there are potential signal killers just about everywhere. Is it always external factors, though? Or can I, the pilot, mess things up too?
Oh, absolutely. And honestly, pilot behavior is often the easiest factor to control, yet it's frequently overlooked.
Like what?
One of the biggest culprits is simply poor antenna orientation. Most controller antennas, even the little stick ones, have some directionality. They work best when pointed correctly towards the drone. A super common mistake is holding the controller flat, or pointing the antenna straight up when the drone is out in front of you or overhead, or even just letting your own body get between the antennas and the drone.
Body blocking.
Exactly, body blocking. It can seriously weaken the signal. Another classic pilot error, flying from inside a vehicle, that metal car or truck body. It acts like a Faraday cage, effectively blocking radio signals. Trying to fly comfortably from the driver's seat is almost asking for C2 problems.
Right, so the scenario. Cold day, doing a property video, decide to stay in the warm truck. Soon after launch, telemetry flickers, control feels weird.
Yep. Risk. Signal blocked by the truck body. Expert action. Get out of the truck. Position yourself for clear line of sight. Make sure your antennas are pointed right. Simple fix, huge impact. Other pilot things include just pushing the limits, exceeding the system's range. Flying further than the manufacturer recommends, even in open space, eats up your signal margin. Or deliberately flying into known shadowed areas behind hills or buildings without a plan B. The sources sometimes use this term link budget, borrowed from satellite comms. Think of your signal like a budget of power. Distance costs power, obstacles cost power, interference costs power. You need enough budget, enough margin to cover the whole flight. Flying constantly with just one signal bar showing, that's risky and arguably non-compliant with the reliable C2 requirement in 901.31. And less common, but still possible, atmospheric conditions. Really heavy rain or dense fog can attenuate the signal slightly, and sometimes weird temperature inversions can bend radio waves over long distances, causing unexpected signal fades or multipath.
That is a serious list of threats. It really sounds like you need constant awareness of your surroundings, the invisible RF environment, even how you're holding the controller.
Exactly right. Which brings us neatly to a related, critical point the sources really stress: latency.
Latency, you mean delay?
Precisely. Latency is the time lag. It's the delay between you making a command input, push the stick forward, and the drone actually starting to move forward. It's also the delay in the telemetry coming back, the time between the drone sensing its altitude and that number updating on your screen. Now, the regs don't specify an exact number, like latency must be below X milliseconds, but TP15263 is clear. Pilots must understand the impact of latency. For manual control, once you get much above, say, 200 milliseconds, maybe a fifth of a second, it starts to feel noticeable. Higher than that, it gets really unsafe really fast.
Why is latency such a big deal? I mean, if the command gets there eventually.
Because that delay cripples your ability to fly safely and accurately, especially when you're close to things or it's windy or you need to make quick corrections. Imagine you see the drone drifting towards a tree. You push the stick to stop it. If there's a 1-second delay before the drone even starts to react,
You're going to hit the tree.
you're going to hit the tree. High latency, even if the signal strength looks okay, makes the C2 link unreliable for safe control. So if you notice a significant increase in latency, that itself can be a violation of the reliable C2 requirement under 9011.31. It means you need to stop, you need to land. Think about using maybe a cellular LTE link for C2 on a really long-range flight. You fly into an area with network congestion. Suddenly, your telemetry numbers are updating like 2-3 seconds late, and the controls feel spongy, delayed.
Yeah.
Risk, unsafe C2 due to high latency. Expert action, abort immediately. Fly back towards better signal or land. Document that latency issue. Or you're flying manually in a TATBot, maybe inspecting a tower on a gusty day. You feel like the drone isn't responding instantly when you try to counteract the wind. Risk. Latency is degrading your control authority in challenging conditions. Expert action. Back off immediately to a safer, more open area. If you can't maintain precise, stable control because of the delay, you have to land. You need to have a feel for your system's normal latency, test it pre-flight, and recognize when it degrades in flight.
So noticing even what seems like minor lag isn't something to just ignore.
Absolutely not. If that lag impacts your ability to control the aircraft safely and reliably, you need to address it or terminate the flight.
Okay, this is, wow, a lot to keep track of. So how does a professional pilot actually integrate all this? The C2 link, the fail-safe, the signal killers, the latency. What are the practical steps? Before, during, after the flight?
It really starts way before you even think about lifting off. The sources, especially TP15263, building on that CRR 901.34 fail-safe test requirement, lay out a pretty clear checklist of C2-related checks that are basically mandatory pre-flight procedures for advanced ops. First up, a proper signal strength test. And this isn't just glancing at the signal bars when the drone's right next to you.
Yeah.
A really good practice, sometimes called walking the dog from the old RC days, is you power everything up, leave the drone at the launch spot, and then physically walk away from it, maybe towards the furthest direction you plan to fly, while watching your controller's signal strength and quality indicators. You need to confirm you have a strong, stable signal with good margin, good buffer, out at your planned operating distance and direction. You also need to check your telemetry updates. With the drone on and linked, look closely at your ground station display. Is everything updating? GPS status, battery voltage, altitude, speed, attitude, signal quality, is it all flowing smoothly, instantly, accurately? If anything's frozen, lagging, or jumping around erratically, you've got a problem before takeoff. Then, perform a quick latency test. While it's still on the ground, just wiggle the sticks. Test pitch, roll, yaw, throttle. Watch the drone itself. Do the motors respond instantly? Does it feel crisp? Confirm that delay feels minimal, well under that rough 200 millisecond mark. High latency on the ground is a definite red flag. Then comes the required fail-safe test. As per 901.34, you gotta test it. If your system allows simulation, trigger a C2 link loss. Watch what happens. Does it correctly start the fail-safe routine you programmed? Does it show it's trying to climb to your set RTH altitude? Does it switch to hover? Does it start descending for land? And crucially, if you're using RTH, double check that the target RTH altitude shown in your software matches what you planned and is safe for this specific site. Next, an antenna orientation check. Seems basic, but make sure your controller antennas are screwed on tight, not damaged, and positioned correctly. If they're directional, point them generally towards where the drone will be. And think about where you'll be standing. Try not to body block the signal path. Then, integrate your site EMI survey findings. Remember those potential interference sources you identified during your site assessment: power lines, radar, cell towers. Factor them into your final checks. Confirm your planned flight path keeps you at a safe distance, or that you have mitigation strategies in place. And last but not least, check your controller battery. Seriously, a controller dying mid-flight is a surprisingly common cause of C2 link failure. Make sure it's fully charged, enough for the whole mission plus a safety margin.
That is a comprehensive pre-flight list just focused on C2 and fail-safe.
It is, and it's necessary for advanced ops. And the sources, they strongly imply, linking back to CRA at 901.27 on maintenance and record keeping, that you absolutely should log the results of these C2 pre-flight checks. Just a quick note. C2 checks complete, signal strong, telemetry updating, fail-safe tested, okay. It's best practice, expected for audits, and invaluable if there's ever an incident investigation. You also need to log any C2 anomalies you observe during the flight after you land.
Okay, pre-flight done meticulously, checks logged, drones up in the air. Could I finally switch on the autopilot for my mapping run and maybe, relax a bit, check my phone?
Absolutely not. This is another huge exam trap and a major point in the regs. CRR 901.31 requires you to actively monitor the C2 link throughout the entire flight.
Even on a fully automated mission?
Even, and perhaps especially, during fully autonomous missions like waypoint flights or grid mapping. You cannot just launch it, verify it starts the pattern, and then walk back to your truck thinking the autopilot makes it safe. That directly violates the continuous monitoring requirement of 901.31. You must remain attentive, watching the C2 link status, monitoring the telemetry stream, observing the aircraft's progress, and be ready to intervene via that C2 link instantly if needed. Keep an eye on signal strength, watch for any hint of increasing latency, be aware of the drone's responsiveness.
Okay, constant vigilance. But if, despite all the planning, all the checks, all the monitoring, the signal bars do drop to zero and I get that dreaded connection lost warning during the flight, what's the exact procedure then?
Okay, first thing, stay calm. Remember, your drone should now be executing the fail-safe behavior you so carefully planned and tested. Your immediate actions are kind of simultaneous. 1. Monitor the drone itself. What is it doing? Is it climbing for RTH as expected? Is it holding position and hover? Is it initiating a link? Confirm it's actually doing the fail-safe routine correctly. 2. At the same time, try to fix the problem from your end. Try to regain the link. Could you move to get a better line of sight if you suspect an obstruction? Double-check your controller antennas. Did they get bumped? Are you body blocking? Can you move away from that power line or cell tower you noted in your plan? Actively try to reestablish solid communication. Now here comes a super critical part, straight from the guidance, often tested. If you succeed, if you manage to regain control and telemetry, you absolutely must perform a test hover and do some control input checks to verify the system's integrity before you even think about resuming your original mission.
So I can't just see the signal bars pop back up, breathe a huge sigh of relief, and just hit continue mission on the screen.
No, definitely not. That would be unsafe. And it wouldn't meet the standard of ensuring a reliable link. Just because the signal came back doesn't mean the whole system is perfectly stable again after whatever caused the drop. You need to bring the drone to a hover in a safe, clear spot. Gently test the controls. Pitch, roll, yaw, throttle. Does it respond instantly? Is it precise? Is the latency back to normal? Is all the telemetry flowing smoothly again? Only if you were 100% confident that full, reliable control and telemetry are back online should you even consider resuming. And honestly, even then, the most prudent thing might still be to just bring it in for a landing and figure out what happened. If there's any remaining sluggishness, any instability, any weirdness, any doubt at all, land immediately. And if you don't regain the link, if it stays disconnected, then the drone has to continue its fail-safe sequence autonomously. Your job then becomes monitoring that automated process as best you can. Keep visual track if possible. If it's heading towards an area with people or other aircraft, try to clear the area as feasible. Basically, manage the situation from the ground as it unfolds according to the plan you set.
And after the flight, if any of this excitement happened, link loss, fail-safe kicking in, major interference, noticeable latency.
Document it. Document everything, especially for professional, advanced, or commercial work. Your flight logs are key. Note the date, time, location, what happened, link loss, failsafe type triggered, interference encountered, latency spike. Describe the suspected cause if you have one, how the drone responded, and what actions you took. This record is vital. It shows compliance, helps you spot trends with equipment or locations, and is absolutely essential if there's ever an audit or worse, an incident investigation. It ties right back to your record-keeping duties under CRR 901.27.
This really paints a complete picture now. It's like a cycle. Intense, proactive planning based on the actual environment.
Right.
Then constant vigilance and monitoring during the flight.
Yep.
Knowing exactly how your system should fail safely because of your settings.
Critical.
And then having a defined professional response ready if things do go sideways, followed by documentation. It's a continuous loop of pilot responsibility.
It truly is. And you can see the thread, right? From the historical necessity of C2 in military ops to it being the major hurdle for early BVLOS in Canada, all the way to today's regulations. Mastering command and control link management, that means predicting and avoiding the signal killers, understanding latency impacts, doing those rigorous pre-flights, actively monitoring in-flight, and critically, taking full ownership of your fail-safe programming and testing. It's just non-negotiable. It's foundational for any pilot operating at an advanced level.
Yeah, it feels like a real mindset shift.
Yeah.
Moving away from just hoping the connection stays green to actively managing all the risks that can make it not green. And being fully prepared with an intelligent, tested, location-specific emergency plan that you put in place.
And what's maybe most fascinating, or even a bit daunting, is how much the whole system relies on your informed choices. Before the flight, during the flight.
Yeah.
The drone itself, it's just a tool. It executes commands you send, or it follows the automated fail-safe routine you programmed. Your knowledge, your preparation, your configuration choices, your testing, your active monitoring, that's what provides the layers of safety. That's what ensures the tool operates reliably and predictably, even when things get challenging.
So wrapping this up, what does this all mean for you, the pilot listening right now, maybe prepping for that advanced exam or already out there flying complex missions? Maybe the provocative thought to leave you with is this. If that command and control link truly is the invisible leash, keeping your drone safe and compliant, especially in tricky environments, how certain are you right now about the actual strength of that leash in the specific place you plan to fly next? How aware are you of the potential threats lurking there? And how confident are you that the emergency plan you packed for it, that fail-safe setting, is truly the right one and tested to bring your aircraft back safely if that leash suddenly snaps?
That understanding, that diligence regarding C2 and failsafe, it's not just about passing an exam. It's absolutely fundamental to every single safe flight you undertake.
Well said. Thanks for joining us for this deep dive into RPAS command and control systems and fail-safe procedures. We really hope this exploration helps you fly safer, smarter, and with more confidence.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.